How's everybody doing? Welcome back to the channel, and in today's video we're hoping to turn this box of bits here into a rotor reflectometer. I've got a number of electronic components, majority of which are from RS components, and we do have a case which is a Nanook 904 case there. For those that don't know, a rotor reflectometer is a specialist piece of electrical test apparatus used alongside an oscilloscope. It's designed to pick up end-to-turn faults on a generator rotor winding. If we look at this picture here of the actual end of a generator rotor winding, you can see the copper turns quite clearly there. Then if you look closely enough, you can see some white strips in between each of the turns. That is in actual fact Nomex insulation strips. And as the generator wears or gets dirty or moves through vibration and temperature changes, that Nomex can become worn and eventually worn completely through and produce a turn-to-turn fault. That can manifest itself in a number of ways on a generator rotor. It might just increase the vibration. It may produce a thermal imbalance on the generator rotor winding. That can cause the rotor to actually bend, and itself can also introduce more vibration. Or it might just be a reduced output from the generator, or a combination of all those three. And therefore we test to see if we can determine if there's any end-to-turn faults, because it's quite a big job to fix those. This actual technique was developed by a Mr. Grant from the Central Electricity Generating Board in the UK way back in 1973. His original paper is available that you can read, and it shows you in there the basic concepts of this and the circuits that he was using to carry out this test. Obviously since 1973 the test has been developed a lot more, and the unit that I used to utilise when I had a proper job was a CDL TDR 100, which was from Convex Designs. Convex Designs then closed down and passed the design over to, or I should say sold the design probably, to a company called Rotest. Rotest developed the 100 and turned it into the TDR 200, which was a digitised version. Now unfortunately these pieces of test equipment are quite expensive. Last time I had a quote from Rotest, it was 12.5k, and by the time me and my useless company had actually saved enough money to purchase one of those, Rotest has actually ceased trading. They ceased trading towards the back end of last year, 2024. So they are no longer available. There is another company out there called Sumatron who do sell a rotor reflectometer. I did get a quote from them for one of these. It comes from America. It's going to be around about £7,500 I think to get one of those into the UK for me. But it doesn't work the same way as the TDR 100 did. And that's the unit I'm used to using. I can't find anything second-hand within the UK, so I thought, given the amount of information I've got both from Convex Designs and from the original paper from CGB, I thought we'd give it a go, see if we can build our own unit up, because they are relatively simple. And if I can do this, I'll save myself quite a few pennies, and that will enable me to put the money that I was going to use to buy a rotor reflectometer into purchasing a 10 amp micro ohm meter. So I'll show you this block diagram. This predominantly comes from the TDR 100RB of its basic functionality. The rotor reflectometer, it fires a square wave signal into one end of the rotor winding and then looks at the reflection coming back from the other end, then switches those connections over and fires a square wave signal in again, and again looks at the reflection coming back from the other end of the winding. It lays those two traces over on the oscilloscope screen, and if your winding is good, then those two signals will match one another. If the winding has faults in it, then those two waveforms will differ and you will see that fault, and to some extent you can also see somewhere whereabouts the location of the fault is within the rotor winding. So that's the basic functionality. What I'll do is I'll get some of these bits assembled up, see if we can get a working circuit on some prototyping boards, and then we'll probably move the design to a VeraBoard for installation into that case. So you can see we have a working model here. I've got my Regal DS1052 picking up the combined double transit waveform at the top, and then the lower waveform is the single transit waveform. There are two ways you can set these rotor reflectometers up. The first one is with a combined double transit signal, as I've got here, which works well with a 2-channel oscilloscope, or we can set it up as 3-channel, where the double transit is split out, and then you can use the maths to do your analysis. I can just show you here, if I stick a little signal on the delay line, that shows you what a fault looks like. So that all appears to be working okay. We can spin it round onto our power supply there. We're running 12 volts and 17 milliamps, 200 milliwatts. So that's all good. I will just show you, because this is 2-channel oscilloscope, and I was saying about 3-channel, which I have my mix sig for. I shall just put him out of the way and put my mix sig. So I did say about using it with a 3-channel oscilloscope, which obviously the mix sig here is 4-channel, so I could do it with a split out signal if I chose to here. However, the mix sig doesn't seem to like to work exactly the same. We've got both our waveforms. It's still 2-channel operation, but you can see I'm not picking up my second waveform for whatever reason. So sometimes these digital scopes don't work very well with the rotor reflectometers. Not sure why, just individual quirks of them, but it works okay with the Regal, so that's the one we'll stick with, and I'll stick with the 2-channel version for now. So we finish off making up the 2 boards. This is a little pulse generator board here, and this is our transistor switching circuit. They've all been relevant holes cut out on them, the components all soldered in, so now I will clear off all the little mess that I've made, and I'll set up and do some basic continuity tests across the 2 boards just to make sure I haven't messed up, haven't forgotten to cut any of the tracks or anything like that. So we've mounted our 2 Vera boards into the chassis here, along with all the controls. Alongside our pulse generator board and our transistor switching board, we've got a power supply board and a charging board. Around this side here we've got a battery holder housing 2 18650 cells. Just put a tie around them just to make sure that they don't come out. I did upgrade the wires on this battery holder here. The wires seem very, very small. I didn't like them at all, so I've upgraded the wires on that. And the rest of it is just all the necessary switching and outlet sockets, and then the control potentiometers alongside there. This front plate, I've made this up using a different technique. This is from a video on YouTube from Accidental Science. I will link that in the description box below, where he's used the printout on an A4 sheet of paper and then sprayed it with varnish and then glued it on. Well, the very first way I used to do these was to print these on the overhead projector screen sheets that you used to get, the clear translucent ones, but you'd have to print that in reverse and then glue that on. I got a bit of trouble with that one, so I then moved to just printing this out on a standard A4 sheet of paper and then covering it with this self-adhesive film that you get from hobby shops, craft shops. I used to do it that way, but that's quite a soft surface which damages fairly easy, so I've tried using his method here to print it out and cover it in varnish and see how we get on with it. I've not glued it on too well there. I've got some like air pockets in there, I presume, but this is just a prototype. This is just to allow me to get out of the site and test a generator rotor with it and make sure that everything is working fine. But what we'll now be able to do is pop this into its little case, and I'll screw it down, and then I'll set a oscilloscope up on the delay line, and we'll be able to see how well it works. We are up and running. We've got both our signals here now. We've got a double transit pulse going out along the top there, and we've got the single transit pulse going along the bottom. So they all appear to be there and present. I can adjust these no problems with my pulse width. You can see him changing there. Dialing off. Pulse frequency, I'd have to change our scaling back for that one there. So change our frequency, see how frequency gets even smaller there. That all appears to be working okay. I don't really seem to use that much, so I might do away with that if I build this into, or as I say, when I build this into its final design, I might well get rid of the pulse frequency and just stick with the width. We can also split the trace down, so I can see the second trace there. You can see that underneath there. So that's all working fine, and then if I put a fault on the delay line, you will see I get my disturbance there at both ends of the screen there of the waveform. So that all appears to be working fine. It's ready to be able to take it out onto an actual generator rotor and make sure that it's working fine on that, which is the main objective of this. I know this is a bit untidy and I've got bits and pieces missing from this. I've not got a I've got a battery charger and input from a USB. I don't have a battery charging light, and I don't have a battery charge status indicator on it either, which need to be added to it. And I need to ensure that the battery pack is large enough for my work. And you can see it's working on the scope quite well. This is the one thing I didn't like with this Regal scope. The screen is a little bit tad short. I've either got this small picture here, which works okay. If I put the fault back onto it, you'll be able to see it okay. It does seem to work all okay, but it's not a very clear picture. It's not as good as if I put it out that way, but then I'm missing the full width of the signal when I do it with that, which is why I tried to get this working on the MixSig. So I will pull out the MixSig and just see if it will start working on that now I've got the design all complete. Back with our MixSig tablet scope, which is what I'd like to have used this with. So you can see I can get the full width of the signal in there now, which is nice, but the flickering that you're seeing there is the flickering I'm seeing. This MixSig, for whatever reason, just doesn't like it as well. I can put the frequency up, but it doesn't appear to be. It's winding up to maximum. Yeah, it's not good at all. If I do the trace switch, you see I don't get both traces. That's not working. If I put a fault on it, you do kind of see it, and I can just see a very faint line here. But it's not working anywhere near as well as the old Regal scope does for some strange reason, which is a shame, but I'll have to have a look. Now that I've built this up and I know it can work, I've saved myself some money. I might see if I can get another oscilloscope with a bigger screen on it and see if that works with it, although we do run a risk if they don't work. But okay, bit of a disappointment with the MixSig, but at least we've got the reflectometer up and running, which is good news. That's our rotor reflectometer all finished off. You see the lid closes up nicely, and we can close the catches on it. So we're all good there. Up till this point, I have spent around about £211 on getting it this far into this prototype. Most of that cost was with RS components, about £84 from them. However, this case here is £60, 22p, so the case is quite expensive. That's a good chunk of it as well. The rest of it I've spent on bits and pieces, plastic and screw sets and stuff like that to be able to complete the build. So with this now, I need to get this out onto a generator rotor and actually test it out live and make sure that it is all functioning correctly. After that, I could look at developing a 2-channel version, so this double transit pulse gets split up into separate channels, and then maybe it will work with the MixSig. I do kind of feel as though I'd like to put this into a larger case so that I can get all the test leads built into the side, stored in there as well, and I do have the test lead set to make up, so that will increase the costs a little bit. I could go down the PCB route and design a PCB for it, but then you tend to get multiple PCBs when you order them in that manner, so I'm left over with a load of spare PCBs which are no longer any use to me, so I'm not too keen on doing that at this moment in time. As I said, we'll see how this performs out on site, but that'll be it for this video. Thanks very much for watching. Hope you found it useful, and I'll see you again in the next one.